Hi everyone. So one more video. This will conclude the tutorials focusing on the TOPS, CHOPS, SOPS assignment. So in addition to the intro to SOPS parts 1 through 3, to conclude all of that, we're going to focus on certain operators that act as bridges between the operator families. And so we can kind of see these laid out right here. We've got things like a chop to top, a chop to sop, a top to chop, a sop to chop, a dat to sop, a sop to dat, and a chop to dat. So say that 10 times fast. Also the first look at what DATs are, we'll look more, going to get a thorough introduction to these next week. For now, we just can notice that they are essentially tables of data. Looks cool. So let's see what these are all about and why would we use them. So up to now, we've done things like chop references. So this little simple thing here, I've got transform, I've got an LFO, which is a square type right now. And it is being referenced over here to rotate. And when we do that, right, we create this kind of Python expression, which says, look at the operator called LFO1 and look at its channel called chan1. So that is teleporting the data inside some operator to be used with a parameter in some other operator. Great. This is different though. What this is doing is actually kind of converting this data into the different form itself. So if we start, maybe I'll just do like a noise to a chop to top and kind of recreate this so we can see how that is working. Chop to, chop to, chop to. Okay, great. And so go parameters. So this, so they all have these kind of field right here. So it's not waiting for a reference. It's like saying, like, I need to know the name of a chop somewhere that I'm going to convert into top pixel data. So we can just drag this over, like the whole shebang. So it's not that kind of like Python script. It's just the name of the operator. And we can see now it has this little arrow. And we can kind of tell what's happening. It's now taking this contours of data and it's converting it into black and white imagery. And how that happened is if I middle click here, so there are by default 600 samples in my noise, and that created a matrix 600 by 1 pixels. Okay, cool. Important to know right now, so data format. So depending on how many channels of data that are coming into it, we can create X number of channels of pixels in our top. So we've only got one channel of chop data coming in. Therefore, we just kind of have one channel here, like R. If I select RG, it's going to give me a little error here. So it says last one channel is unused. Because it's expecting 2 channels of data, but we're only giving it 1, so therefore it's confused. So there's all these things. So alpha, so where this is close to 1, that's alpha. I mean, let's just go back to R just for clarity. When there's only 1 channel of data, so it's not just R. It's going to be mono, right? It's just grayscale. When it's close to 1, that is white. When it's 0, that is black. These spots where in the chop data it goes below 0, that essentially gets kind of just clamped off. So the black is black here. So I might, in order to have a little more meaningful data, I might actually, do something like, I mean, if I wanted to. Okay, let's learn something else too while we're at it. To double up things we're learning. So let's, instead of doing that, let's reference null1. And that's because I'm going to add a limit chop. It's another little side lesson here. So a limit chop can kind of clamp the data in various ways or limit it. So minimum, let's say, there we go. Because that's essentially what the top is creating anyway. So just visually, we kind of get a better sense in our chop data of how that's going to be translated into pixel values. Okay, cool. Or I could have just done positive only. So if that did -1, what if I did positive only? Yeah, there we go. So they kind of automatically, instead of clamping it, it kind of looped it back up. So different ways. There's always a million different ways we can do the same thing in Touch. Let's do something. Let's bring that up a little bit. Okay, that's good enough. And just for the hell of it. Sure. Okay, great. So we can kind of see how that's happening right there. Also, let's look. So one thing, it's in this kind of zone. It's not quite the first thing you need to know about, but it's good to know. It's this format, 32-bit float, mono. Let's go over to common and pixel format. Here we go. So here we see some pixel formats, 8-bit fixed RGBA, 32-bit float RGBA, because this is saying it's 32-bit float mono, right? So that's essentially this down here. So the difference in that is 8-bit fixed means the pixels will be restrained in the value from 0 to 255. So that's like a typical digital images that you are used to working with are usually 8-bit images. So for RGB and alpha, they have values from 0 to 255. Great. Fixed means it can't possibly go lower than 0. It can't possibly go higher than 255. It's 8 bits of data. That's it. So the chop to top here, by default, it kind of goes to this 32-bit float mono. So it's one channel of data here, but 32 bits means it's 2 to the 32 power, which I did the math. I forget what it is. Feel free to do that on your calculator. It's a whole lot more increments from the darkest dark to the brightest bright. Therefore, the image ends up being like much more resolute with smooth gradations from the darkest dark to the lightest light. Great. And not fixed, it's float, meaning it can go less than 0. Actually, it can go high. There's a kind of mathematical limit to that, but it's never really going to clamp off the ends of that, the darkest darks and the brightest brights. It's going to allow things to really flow and have great resolution. So that's something to keep in mind. Just further down the chain, it might be useful to understand what pixel format is. By default, use input is just like this, so it's just creating 32-bit float. Great. So what if I want to add more colors to this? Or maybe before I do that, like I don't know, what would I use with this? I don't know. Common thing to add after this is a fit top. And with a fit top, we can go into common here. We can just tell it what resolution we want it to be. Let's just do our old 1280 by 720. And let's fill. Okay, that's cool. So we went from 600 by 1 to 1280 by 720. So we're expanding it larger than it is, obviously. So we're gonna get some blurriness in that, but that looks kind of beautiful, actually, right? If we wanted to keep in mind the resolution, like in our whole chain, if I know, like, okay, I'm going to create something that's 1280 by 720, I could think ahead of myself here. Go back into my noise. So this has 600 samples, right? What if I just was a little proactive here? And I could go into these other tabs, and here in channel, this is where I'm setting that sample length of 600, because start is at 0 seconds, end is 10 seconds, sample rate of 60 samples per second, so that equals 600, right? I mean, I could change this to samples if we want. I don't know, what if I did 1280? So 0 to 1279 means there are 1280 samples total. So again, I means samples. The frames is basically corresponding to this weird timeline thing that's always looping. between first frame and the 600th frame. Don't have to worry about that too much right now, but frame rate is 60 frames a second, so that's how we get this kind of like time length, which is kind of weird. Okay, I'm cool with that. So now we can see this kind of got a little more fine detailed, which is kind of cool. Okay, I want to add some like other channels here. While I'm at it, instead of just calling this chan 1, like I know down the road I'm gonna convert this to RGB. So why don't I just do that here? I'm gonna, instead of chan 1, I'm gonna call it RGB. And voila, we like automatically created 3 different channels of noise. What happens is it kind of starts with seed 200, and then the next channel has a slightly different seed and a slightly different seed for each channel, so they end up being different, but they have the same parameters like here. So that's pretty cool. Also, there's different ways we can view this. Again, for all these things, we can make viewer active, right-click, and we can see some cool other things here, like number of graphs. I like this. All channels in a single graph. So that kind of overlays all those. So that kind of makes it more easy to see the differences in each channel, I think, and to compare their highs and lows. Again, middle mouse click, and then I'm scrolling up and to the right, or left and down. So this is kind of zooming vertically and horizontally. Left mouse click to just kind of drag that around. Right mouse click doesn't do anything. If I right click again, I could do dot per sample. Just scroll in some more. So this shows me a dot every time there is a sample in my data. So this, this makes very clear this kind of conversion. Okay, the chop data is really just a collection of samples that have a certain value. That's all it is. And then down here, by default, so units, by default, this shows us frames. I could say it's samples. So it's going to show us from sample 0 up to sample 1279. If I just go over to the edge here, we can see the edge. Dun, 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 dun. We're going. Okay, there we go. Right, so it goes up to sample 1279, and then it just kind of would loop after that. It doesn't do anything else. Okay, to get it back to our kind of default view, we can right-click, horizontal adapt, vertical adapt. I'll get rid of dot per sample. Okay, great. And I've got it limited, end with a null. So, I mean, this is also why it's good to end with a null. Whenever you're doing any sort of references or dragging things over, just go ahead and make a null, because then you're like, oh, I want to add a limit chop or some other operator. Like, what if I want to suddenly add a math chop right in there? I can just do that, right? As long as the null is the one that's being referenced, so it makes it easy to like add other things downstream. Now, so we've got 3 channels here. Let's go back to our chop 2 data format. We could do RGB, and then all of a sudden, right? So this is converted to red. That's green. That's blue, and we've got different colors here. So that's pretty cool. A little bit loud, but whatever. And then to reinforce that absolute time.seconds thing, if we look at another tab in the noise here, transform. So sparse, this type of noise is actually, if you think of it like a mathematical entity, it's 3-dimensional, which means we can translate in the X, Y, or Z dimension. So if you imagine like the noise, the random numbers as being a kind of loaf of bread, we can translate through the X or Y or Z to change that. So to show you that, so let's do translate. We can go through. Kind of scrolling through that. So by changing that translate X, it's kind of just scrolling like that. Cool. What if I did Y? So that's a little more dramatic. Cool. And then Z. Right, so all of them are kind of just shifting. So you imagine it's kind of like going through that loaf of noise bread. So maybe I'll translate the TZ. So I'm going to hit this little plus, hit the blue box to write an expression. And again, ABS, capital T, time, dot, seconds. And that is counting the number of seconds it has been since this file in Touch Designer was opened. And that's going to give a nice sort of slow fade. We can speed that up with times some number, or we can slow it down by times 0.1, let's say. So now it's super slow. I'm cool with just the way it is. And now that our noise is changing, let's do that a little bit faster actually. Times 5. There we go. So that's, we've got a little bit of a shimmer type of thing happening there. Okay. I mean, of course, we can just change all this stuff to our heart's content. Big period. That actually looks a little bit better, like a little less just kind of colors all over the place type of thing. So kind of like that. Let's make that a little bit faster actually. Okay, cool. So now that's going to be a slowly randomized shifting abstract type of thing. Love it. Okay. So what's happening with these other ones? So Chop 2, it's taken that same data and instead of converting it to pixels, it's converting it to a geometry data, which is super cool. Let's just do that over here. Let's do SOP. Let's do Chop 2. Drag this over. Because it's saying, which chop do we need? It's got some other info we don't need to care about right now. Okay, so this is giving error. What's it saying? Channel TX not found, TY not found, TZ not found. By default, we need to look at channel scope, attribute scope. Channel scope is saying like the channels called this in the chop are mapped to the attributes of my geometry, which is P0, P1, P2, which is, we can see here, point position X, point position Y, point position Z. Of course, we do not have channels called TX, TY, TZ here. We have channels called RGB. So let's change that. RGB. And that's pretty cool. Okay. So the red channel gets mapped to the X position. Green is Y. Blue is Z. Okay, pretty cool. We could, and one sample to each point. So again, if I middle click, there's 1280 samples, and then guess how many points I have here. Yes, 1280 points. Beautiful. And again, I can click that, right click, display options, points. I could see point numbers if I want to. And if I want to zoom in, pause. So there we go. We see the point numbers here. So it's all kind of lined up there. Great. I'm going to go ahead, home all. Great. Okay, so what if I did, I could do the same thing I talked to the other one. Let's do like, I don't know, wireframe maybe. Make it kind of skinny. Play with these other end caps, fast wire. I think from there I might need to do an attribute create. There we go. Compute normals. Because it was not creating normals from this. Remove polygons. Oh, here. I didn't compute normals on there, so I should have done that. Do that. So you can see I touched a little bit on what normals were. Let me turn that off again. If I do that, let's do display options again. Point normals. And we can see there are no normals. So do that, back to the chop to SOP, compute normals on. Great. So here we actually see all the normals now. So these are all pointed in one direction, actually, which is interesting. So the normals are responsible. So there's usually one normal attached to each point, and it tells whenever there's lighting in the scene, depending on how that point normal is pointing, let's say light's here, point normal is facing like this, that computes how the light is supposed to bounce off of that surface. So if the normal is pointing this way, it bounces differently versus that way. So it's all about kind of calculating light reflectivity and how light bounces around a space. I mean, that by itself, that's kind of cool, actually. I kind of love that. So I can't help myself. Another digression. There's another top called OpViewer. So it can directly translate any viewing display into an actual top. So I'm going to just do this. Look at this. Boom. Awesome. So now like the actual display of my SOP with the normals being shown has been converted directly to pixels. So that's kind of crazy. That's so this would be a kind of that would be a shortcut, I guess. It's not something you should do a lot because it's kind of intensive computationally. Normally we would do the kind of geometry comp, camera, light, render top, and go through that whole process to turn it into a top thing. But that just looks pretty cool, I think. I love it. Okay, so you can play around with all of that to your heart's content. Over here, just briefly, we can show also the SOP to DAT. Just to show, right, I'm looking at, so this thing here, it's extracting points, vertices, primitives, detail. Right, so with points, it's got, okay, what is the point index, X, Y, and Z value, point weight, which kind of corresponds to a kind of thickness of the point, and groups, which there's other SOPs that we can actually group pixels, but we're not going to, or points, I should say. Don't worry about that right now. Okay, next. How about top to chop? So it's kind of the opposite of this situation here. We can kind of see what's happening. Let's just maybe look here a little bit. So I've got this still image coming in, movie file in, and so it's looking at these channels of the top, and I'm creating these channels. It could be, named whatever you want. Radish. What's a vegetable that starts with G? I can't even think of it. Gargle. I'm just like making up these things, whatever. So point being, it's arbitrary, right? To me, it makes sense to give it a name that is actually a description for what it does. If we look at, okay, so it's not actually translating all of the pixels because if we look at this image, it's 1920 by 1080. So there are over 2 million pixels in this. But there are only 1920 samples in my chop. If I end up with something with like 2 million samples in a chop, then that's liable to crash things. It's going to be super huge, right? To show that, let me just do something a little crazy here. Let's do resolution. Let's do like 3 by 3. And let's do input smoothness, nearest pixel. Okay, let's do that. Okay. So I just turned off input smoothness, or say viewer smoothness is just affecting the viewing display. This input smoothness is actually changing the actual video signal. So let's just do nearest pixels. Great. And let me do the same top to situation. So this is a little bit more manageable. So I could conceivably crop. So here in the crop thing. So by default, it only does a single row. So if we look, let's see, it's doing U start, U end, V start. So let's look at this here. Viewer active, right click, display pixel values. So it's kind of easy to look at. I only have 9 pixels in the entire thing, but you can see how U and V change. So U and V U corresponds to horizontal or X value. V would correspond to the vertical value. So down here, U and V is 0, 0, and U goes up like that. And here V goes up. So right now, I'm grabbing the row, which is the V start 0.5. So I don't know. I don't know which one it's grabbing. So 0.5 is like in between this. I don't know, maybe it's grabbing this one. I can't really tell. This makes more sense, like interpolates when the image is pretty big. But it's a V start. Let's do 0.333. We do pixel. Oh, there we go. Yeah, we can select individual pixels. That's cool. So this is just grabbing. Okay, there we go. So that's changing now. Let's do the same thing. Let's number of graphs, all channels in single graph. Okay. So as we change this, we can kind of see. Right, there we go. Those values change. All right, great. So that's just doing one row. I could do one column, and then so it's giving me this U start. So now I'm just grabbing one of these columns, grabbing values from it. Or I could do full image. So now we can see, so this gets kind of wild. Let me go back here. Oops. All right, so it should be 3 different channels. So that's red 0, green 0, blue 0, alpha 0, red 1, green 1, blue. So it's creating a whole lot of different channels because it's getting the entire image. So it needs 9 different. So each of these has red, green, blue, alpha. So times 9. So do the math, genius. That should be 9 times 4 is 36. So there should be 36 channels here now. So that would quickly be exponentially unfeasible once if you had an actual image that was kind of larger. But you can, if you have an image that's really tiny, you can play around with that. Rows and columns. So you can kind of choose different rows and columns if you want to play with that. Cool. By default, just this is used. So here we can kind of see, where am I grabbing here? Crop. I'm doing. So if V is like 0.5, it's essentially like a row, like right in the middle, right here. So it's getting those values here. As I scrub through, you can see the values change. So that's kind of cool. This is just showing, again, chop to dat. So we see like all those values change. That can be useful down the road once we learn more about DATs. And then we could do something like, let's drag this over here. Let's do some sort of SOP visualization here. Let's do a chop to, chop to. Let's look at that. And again, this gives me an error because it's looking at TXTYTZ. And let's just look at one channel for now, red, and I'm going to convert that to Y. Beautiful, there you go. So this red channel is being converted to the Y value for the points. Up here, start position, end position, so it's already doing it kind of on the X. It's starting at -1 and going to +1, so that's why it's spread out like that. And so I'm only looking at kind of mapping to the Y over here. And the Z is not really doing anything. It's just kind of flat, as you can see right there. So I could do something like, create a kind of cool visualization thing. If I had like, I go in here, I do geometry for each of these. Let's say I do like a font, get like a reddish color. Get my camera, I get my light, I get my render, and let's say I just kind of copy this situation, boom, boom, right? I could do one for green, one for blue, each chop to SOP. I'm looking at a different thing. So here maybe I'd look at green instead. Change that to green. That's kind of green. It's kind of yellowish, right? Good enough. Okay. Here would be blue. Chop tube, looking at the blue channel instead. Okay, great. Why not just go ahead and do this? I'm curious to see how this will look. And let's get a render. Let's make that a little bit brighter. Okay, that's kind of interesting. You know, I could do a little bit of a shift if I want, like a translate. Yeah, translate this one down. Okay. So now what if I had LFO? Let's do offset 0.5, amplitude 0.5. So now it's going from 0 to 1. Great. And let's just cycle through the V. Let's see what happens. Too fast. Okay, so that's something, right? I'm going from an image. Let's keep going here. Let's do an over. So that would go on top. Let's say the image comes back in over here. Let's end that with a null. Okay, so it's a kind of histogram analysis of the image on top of the image itself. Cool, all right. Okay, and some other ones. So this one I don't use as much, but you know, SOP to chop. So also is kind of taking the points of any SOP geometry. So we can see there are 722 points. Translates that to TX, TY, TZ over here, and you guessed it, there are 722 samples now. So depending on what this is, you can kind of create interesting contours of data and then use that for other things. Like I actually kind of like this, this TZ or the TX is an interesting shape. So I could, use that for like a brightness or some other value down the road. Kind of just the shape of it is kind of interesting, I think. So it could be an interesting way for you to get some sort of contours of data. And then this last one is a DAT to SOP. So what's happening here, let me do the same thing here. Points, let's do point numbers. I've just manually written a table DAT, which we'll get into more next week of how to do this and why we would do this. I've got 3 columns, so these correspond to, as you guessed it, X, Y, and Z coordinates. So this row is 0.0, this is 0.1, 0.2, 0.3, 0.4. So we kind of see those right there. So if I did something like, let's do the 4, let's increase the Z a little bit. There we go. So that moved out there. Cool. So that's a kind of interesting little thing. Just kind of generating geometry from scratch just by typing in numbers. There's lots of different settings we can do for this. Connect all points. Let's see, like some of this you need more kind of info than we're dealing with. Particle system, the points are so tiny though. It's really, I think just connect all points is the coolest one, just right out the bat. All these other things kind of require a little bit extra know-how to input things. But this can be kind of cool if we follow this up, let's say with a wireframe. Okay, cool. And because this is not creating normals, right? So maybe I'll do that thing again. So I'm actually using an attribute create, which is a useful little thing. Compute normals. There we go. So you can see what happens when I compute normals. It actually responds to this kind of lighting in the. There's even before you add a light, there's a kind of default kind of lighting just for the viewing displays. So that is now showing up. So okay, that's kind of like a cool sculpture or something, right? So you can place that in a scene somehow. It's an interesting idea to kind of create sculpture, just by typing in some numbers, let's say. Okay, so that is a hot mess, but some other, just a lot of other tools that you could use for, translating data between these main operator families that we're working with. For the assignment, it's really just focusing on, throwing all these things together and ending up with something visual. All right, cool.